We now return to magnets on Modern Marvels. There's a magnet in Florida attracting the global scientific community. Housed at Tallahassee's National High Magnetic Field Laboratory, it's the largest and most powerful magnet in the world. It generates a magnetic field about 1 million times greater than the Earth's, making it an invaluable research tool.
Well, the mission of the laboratory, the primary mission, is to conduct science at very high magnetic fields.
The main reason that we seek out these very, very high fields are much the same reason we might measure things at very high temperatures or very low temperatures, very extreme conditions. When you move to new areas, just like Captain Kirk and Captain Picard, when you go where no one has gone before, you are bound to learn some new things.
The jumbo magnet's awesome force results from the combined power of a giant electromagnet and a nitrogen and helium-cooled superconducting magnet. It's so strong, it can actually levitate materials that you wouldn't expect to react to any magnet. This is possible because most common materials, including water and living tissue, are weakly magnetic. They're said to be diamagnetic, meaning they exhibit a subtle tendency to be repulsed by a magnetic field. One intriguing way to demonstrate this diamagnetic force, as well as the unparalleled power of the lab's magnet, is to enlist the aid of an ordinary frog.
Frogs are 90% water, and water's diamagnetic. And let's imagine what happens when we bring a frog near the center of a high magnetic field region. When we do this, the diamagnetic force on the frog gets larger and larger.
It may look like the frog is floating in water, but it's actually suspended in the air. The magnetic field being generated is so intense that it's canceling out the force of gravity. A magnet's power of levitation over everything from frogs to frying pans represents much more than an amusing parlor trick. It offers a world of tantalizing commercial possibilities.
Say you have machinery that you want to spin very, very fast, and ordinary ball bearings won't do because there's too much friction. You could levitate. They're called magnetic bearings. You can levitate the shaft and allow the shaft to rotate it in a magnetic field.
A racier form of magnetic levitation is scorching its way along a 12-mile test track in Emsland, Germany. Here and in Japan, maglev engineers are developing frictionless rail systems that propel trains at speeds up to 275 miles per hour. Wondering how you levitate one of these 60-ton rail cars? The bottom section of the train wraps around a T-shaped track called the guideway. A set of electromagnets lines both sides of the train's undercarriage. An electromagnetic field generated in the guideway attracts the magnets, lifting the train less than half an inch above the track. A second set of magnets lining the train's sides exerts a lateral force, keeping the vehicle properly aligned. If you're looking for the motor that propels the maglev forward, don't bother looking anywhere on the train. It's laid out flat along the guideway. A system of magnets, like that used on Magic Mountain's Superman roller coaster.
This is, for example, another application of the linear synchronous motor. If you synchronize the changing of the poles with the motion of the train, you can keep the forces going.
Train engineers aren't the only ones getting a lift out of magnetic levitation. Scientists at NASA are exploring how magnets can give the spacecraft of tomorrow a boost into orbit.
One of the things that we're investigating that deals with the use of electromagnetic energy is a launch assist system. And this is a ground-based electromagnetic rail with levitation coils and a linear motor that provides thrust to give a launch vehicle the initial velocity from dead stop up to 400 to 600 miles an hour. We have no contact with the ground due to the levitation, and then the linear motor provides the acceleration and the propulsion in the forward direction.
A magnetic levitation launch system would conserve a huge amount of fuel. Fuel that would otherwise be needed to escape Earth's gravity could then be available to propel a craft deeper into space. But some believe magnet technology will play a far more significant role in our quest to reach the stars. Within the next few decades, space propulsion systems could be fueled by superheated gases called plasmas, and magnets may be the key to containing their immense energy.
The particles inside the plasma are charged particles that have very high kinetic energy. That means they're moving. Moving charged particles create a magnetic field. So that means a plasma is magnetic and will respond to a magnetic field.
Experts theorize that magnets would be the only force capable of preventing the superheated plasmas from burning through the walls of the propulsion system. And only magnets could safely direct the plasmas to reaction chambers. If such a system could be engineered, it would power a bold new age of exploration.
This concept would eventually lead to enabling humans to go anywhere in the solar system anytime they want to go, and at reasonable cost.
From the cosmos to your computer. From roller coasters to your refrigerator, magnets exert their invisible yet indelible influence. They surround us and empower us as a crucial driving force in our lives.